This is SP Gubbi online classes. Welcome to Sangam tutorials for mathematics and science classes for SSLC and CBSE 10th standard. So in the previous session of physics, we had learnt regarding the ray diagrams connected to the convex lenses. So we came across some 6 ray diagrams continuously. In the first ray diagram with respect to convex lenses, we went with, just we recapitulate all the things. This was the principal axis, the object was at infinity, so the light rays coming from the object passed through the lens and the light rays got refracted and they met at a point on the principal axis. So the image was formed at F1, that is F2. Let us take it as F1, this is 2F1 and this is 2F2, okay. So the image was formed at F2, so the image was highly diminished, it was very highly diminished and it was real and inverted because it's a point where actually the two light rays are going to meet. So this was the point where the image was formed, okay. So next the object was brought near to that is near to 2F1. So if you take that as the ray diagram, so you can see here this is the optic center, right? So this is F1, this is 2F1, this is F2, this is 2F2. So the object was kept somewhere here beyond 2F1. So two light rays were taken from this point A. Right, so one light ray passed parallel to the principal axis, passed through that is the lens got refracted and it passed through the F2. Right, another light ray was going to pass through the optic center of the lens. So the image was formed somewhere here. So between F2 and 2F2. So as you brought the image near, that is object near to the lens, the image went far away from the lens. So here, when you compare the size of the object with the size of the image size is decreased. That is, the image is not as big as the image, it is smaller than that. So, the image is real and inverted because it is formed at a point where actually the two light rays meet at this point. So therefore, it is real and inverted. So next is when you will take another convex lens. So this is the principal axis. Optic center, this is F1, this is 2F1, this is F2, this is 2F2, right. So now exactly the object was placed at 2F1. So you can see here it was beyond somewhere 2F1, that is infinity. So it was beyond 2F1 and this second, this one, the third ray diagram, we have kept the object exactly on 2F1. So one of the light ray was taken parallel to the principal axis, it got refracted and it passed through the principal focus. Another light ray was made to pass through the optic center. So the image was formed exactly at 2F2, which was of the same size as that of 2F1. So here also the image was real and inverted. Right. So in the next ray diagram, we bring the object still more near to the optic center. This is 2F1, this is F1, this is F2, this is 2F2, okay. So object was kept in between, that is 2F1 and F1. So one of the light ray was made to pass through parallel to the principal axis. After refraction, the light ray will pass through the principal focus. So another light ray was made to pass through the optic center of the lens. So these light ray met somewhere here, somewhere which is beyond 2F1. So when compared to the object, the image is highly magnified, it's a very big image. So when the object was kept exactly at F1, this is 2F1, this is F2 and this is 2F2. So when the object was kept exactly at F1, one of the light ray was made to pass through the principal axis, parallel to the principal axis. So after refraction, it will pass through the principal focus. So another one is the light ray which is made to pass through the optic center. So both the light rays were exactly parallel to each other, and these two light rays, according to physics, we say that two parallel light rays, they meet each other at a point after a very long distance. We say that that point as infinity. So these two light rays meet at infinity. So if you consider this point as infinity, then the size of the object is very big. So when compared to this, right? So this was the fifth one. So we'll go with the sixth ray diagram, which is very important. So this is a convex lens. This is F1. This is 2F1. This is F2. This is 2F2. Right? This is the optic center. So the object was kept in between the optic center and F1. So now the light ray was made to travel parallel to the principal axis. So after refraction, the light ray is going to travel through the principal axis, that is principal focus on the principal axis. So another light ray was made to pass through the optic center. But these two light rays are diverging. So you can see here the distance between the two light rays is less. So here if you see that the distance between the two light rays is a little bit more. So if these two light rays are drawn like this, they move more and more far away from each other. So therefore, these two light rays are said to be called as the diverging light rays. So in this case, will the two light rays meet at infinity? No. At this case, the two light rays will never meet each other. So therefore, the image formed here is taken. That is, the light rays are taken back. They are taken back like this. So an image is formed here. So this is A dash, B dash, and this is AB. So the image is formed due to the where the light rays are being drawn backwards and they are made to meet each other. They appear to meet each other at this point. So at this point we say that the image is formed. So here the image is that is virtual and it is erect. So therefore, from these ray diagrams we can come to a conclusion that convex lenses gives real and inverted images which are bigger than the object, which are lesser than the object, and also equal to the size of the object. And also the convex mirrors gives virtual images where these images are bigger than or magnified than the size of the object. So here you can see AB is the size of the object and the image, virtual image is A dash B dash, which is bigger than that. So here this is used in astronomical telescopes, this is used in cameras, and this one is used in terrestrial telescopes. This one is used in cinema projectors. This one is used in searchlights, and this particular phenomenon of lenses, arrangement of lenses, are used in microscopes. So you have to remember the uses of this. So what are the characteristics of the images formed by convex mirrors? The convex mirrors are going to form images where they are real and inverted. Most of the times they are real and inverted of say of the same size, of the less size, and the bigger size when compared to the object. And at last, the convex lenses also gives images which are virtual and erect, which are magnified. So that is the sixth ray diagram. I hope this is very important. You have to remember this, right? So in today's class, we will be going with the ray diagrams connected to the concave, that is lenses, concave lenses. So only two ray diagrams are available for concave lenses because concave lenses forms just two images. So one is when the object is kept at infinity, how the images are formed, and the second ray diagram will be when the object is kept anywhere in front of the lens, So let us go with the ray diagrams. So this will be concave lenses, right? So when the object is kept at infinity. So what happens in a concave lens when the object is kept at infinity? How the image is formed. So here we can recall the definition of a concave lens. A concave lens has two refracting surfaces where both the refracting surfaces are spherical in nature, but which is thin at the end and which is thick at the edges. So this is called a concave lens. So here the point at which the light ray, when passes through the concave lens, which passes undeviated, is called the optic center of the lens, that is represented by O. So let us draw a line connecting the two center of curvatures of the lens. So let us call it as F1, let us call it as 2F1. This one is F2 and this is 2F2, right? So here, when the object is kept at infinity, means we'll take an object which is kept at infinity here. So we'll take this as 2F1. So let one of the light ray pass through the lens from the infinity parallel to the principal axis. Let us make this light ray travel parallel to the principal axis. So this is the light ray traveling parallel to the principal axis. So according to the rules, the light ray as it enters from a rarer medium into a denser medium, at this point it is going to get refracted and this is going to get deviated. The light ray is going to get deviated because concave lenses are diverging lenses. So therefore, whenever the light rays are incident on the concave lens, the light rays are going to get diverged. Okay, let us take another light ray traveling parallel to the principal axis. So it falls on the lens. It is going to get refracted. That is, after refraction, it is going to get diverged. So in this case, these light rays are, as they are diverging light rays, they will never meet each other. So therefore, we draw these light rays backwards in the backward direction, and we see that these two diverging light rays exactly start at the principal focus, that is F1. So here we say that the image is formed at F1. So here the refracted light rays appear to meet at the point F1. So therefore image is formed at F1. It is formed at F1. So the image is point size. It is highly diminished. Highly diminished, or you can write point size. Point size. Okay. So these refracted light rays, as they appear at this point, we say that the image is formed at this point. So when two light rays appear at a point and we say that the image is formed at that point we say that the image which is formed is virtual and erect. So the image is virtual and erect. The image is virtual and erect. So this is what happens when the object is placed at infinity. When the object is placed at infinity in front of a concave lens, the image of that object kept at infinity will be formed at F1. That is, it appears to form at F1. Okay. So let us go with another ray diagram. At any point from optic center. At any point from optic center, right? Let us take this. So here you are supposed to keep the object anywhere in front of the concave lens. Anywhere you want in front of the concave lens. It is beyond 2F1 or at 2F1, between F and 2F1, or at F1, or between optic center and F1. Wherever you keep the object, it doesn't make any changes. So let's see what happens. So this is a concave lens. This is a concave lens, right? So this is the optic center of the lens. Let us join the line connecting the two center of curvatures through the optic center. So this is F1 and let this be 2F1. So the distance between optic center and F1 should be equal to the distance between F1 and 2F1. So the same distance should be maintained here also. So that is, this is F2, the same distance, that is 2F2, right? So now let us keep the object anywhere you want. Anywhere you want, you can keep it. So you keep it in between 2F1 and F1, or beyond 2F1. Okay, anywhere you want, you can keep it. So let us take the object as AB. Now let us draw two light rays. One light ray starting from point A and parallel to the principal axis. So this line should be drawn exactly parallel to the principal axis. So according to the rules, whenever the light ray enters from a rarer medium into a denser medium, it undergoes refraction. So due to the refraction, there is a change in the direction of the light ray. So the light ray is going to get diverged because the lens what we are using is a diverging lens. So let us take another light ray. Let us make it to pass through the optic center. So whenever the light ray is made to pass through the optic center, we know that the light ray is going to pass out of the lens undeviated. So this light ray is going to pass through the optic center undeviated. Okay. Now, so where does the image form? That's the very important question here. Where does the image form? So let us draw this diverging light ray backwards. Let us draw this diverging light ray backwards. So here it meets this light ray at this point. So here we say that the image is formed at this point. So this is A dash and this is B dash. So wherever you keep the object, anywhere you keep it at 2F1 or between 2F1 and F1 or at F1 or between O and that is optic center and F1, the image will be formed between F1 and optic center. So the image is formed here. So when you see the image, size of the image and size of the object, when you compare the sizes, we can see that the size of the image is diminished when compared to the size of the object. So between, let us write the characteristics. So it is formed between F1 and O, that is optic center. So it is diminished. So here actually two light rays are not meeting at this point because the diverging light ray is pulled back and made to meet this light ray. So at this point the image is formed. So therefore the image appears to form at this point. So therefore it is virtual image. So virtual images are always erect. So it is virtual and erect. So these are the characteristics of. Okay. These are the two possible ray diagrams for concave lenses. Very important that ray diagram is asked for 1 mark as a 1 mark question. So here in this ray diagram we can see that we are going to come across some numericals based on this. So please understand the concept behind the ray diagram and apply when it is needed. So knowledge is very important. So please remember this. The size of the image is always less than the size of the object in case of a concave lens. So it is virtual and erect. This is very important. So it is always found between F1 and optic center. So these are the characteristics you have to remember. Okay, let us get into the next concept. That is, let us go with the most important thing. That is sign conventions. Sign conventions for lenses. Right. So the sign conventions for lenses are going to get applied for both the lenses, that is convex lens as well as concave lens. Irrespective of the lenses, they are going to get applied. So here sign conventions, we have seen that in mirror also. So sign conventions in lenses we are going to come across now, which is very important. This is required for solving numericals on lenses. So sign conventions for lenses are also called as the Cartesian sign conventions for lenses. Very important. Let us go with this. So to learn the sign convention for lenses, let us take the help of a convex lens. I will take a convex lens. This is the optic center. So this is the center of curvatures. We will join the center of curvatures. Right. So this is F1 and this is 2F1. This is F2 and this is 2F2. Right. Now this is a convex lens. So for example, I have kept the object here at this point. Let us call the object as AB. Now the light rays are falling on the lens in this direction. That is, light rays are coming and falling on the lens in this direction. So whatever the measurements you do, the rule number 1 I am telling you, rule number 1, according to rule number 1, whatever the measurements you do with respect to a lens, all the measurements should be done from the optic center of the lens. Remember this, all measurements should be done from the optic center of the lens. Now, so AB is the object what I have kept here at a certain distance from the lens. As this is the optic center, the distance of the object, AB is the object, the distance of the object from the optic center of the lens, it should be measured in this direction. But the light rays are moving in this direction, so therefore you are measuring something against the direction of the light rays. So therefore this measurement what we take here, that is OB measurement, this is the object distance. AB is the object, the distance of the object is measured from the optic center of the lens, and this object distance, as you are measuring against the direction of the light rays are moving in this direction, you are taking the measurement in this direction. Therefore this object distance, which is called as U, object distance is always measured by U, will be always negative, because you are measuring the distance of the object from the optic center of the lens in the direction opposite to that of the incident light rays. Therefore that measurement is taken as negative, right? So therefore object distance here it is negative. Now I want the height of the object or the size of the object. Height and size are both same, as like in mirrors what we used to speak out. So in the same manner here also, the size of the object or the height of the object, right, it has to be measured. So now as you are measuring this above the principal axis, you are measuring something above the principal axis, therefore this height will be called as H and this will be positive. Anything you measure above the principal axis is taken as positive. Anything you measure against the direction of the incident light rays is taken as negative, right? For example, let us take image is formed somewhere here. Image is formed here. So that is A dash and B dash is the image formed. So you know, you are well aware of the ray diagrams. So that is where the image will be formed when you keep the object in between 2F1 and F1. Okay. Now I want to measure the distance of the image formed from the lens. That is, I want this measurement. This measurement, that is, image distance is represented by V. As like in mirrors, same symbols we are going to use in lenses also. So this is the image distance. So here, whatever we measure, it should be measured from the center of the lens, that is the optic center. So here, as we are measuring OB dash, it is measured in the direction of the light rays. Light rays are in this direction, that is in this direction. You are also measuring the distance in this direction. Therefore, as you are measuring the distance of the image from the optic center in the direction of the light rays, therefore this is taken as positive. That is, image distance is taken as positive. So this is very, very, very important. So once again, let us go with the sign conventions. So one more thing I will conclude. So here I want the size or height of the image. If I want to measure the size or the height of the image, that is represented by H dash, as we used to represent in mirrors. Same thing happens here. So as you are measuring this distance below the principal axis, therefore this measurement is taken as negative. So whatever you measure above the principal axis is positive, whatever you measure below the principal axis is negative, whatever you measure against the direction of the incident light rays is taken as negative, whatever you measure in the direction of the incident light rays is taken as positive. So these are the sign conventions you have to remember with the symbols. So symbol for object distance is H, symbol for image distance is H dash, symbol for object distance is symbol for image height or size of the image, size of the object is H, that is size of the image is H dash, represented by H dash, and the distance of the object from the lens is taken as U, distance of the image from the lens is taken as V. So now in this case, is, as you are measuring something against the direction of light rays, U is negative. H is above the principal axis, therefore it is positive. From here to here, image distance, you are measuring in the direction of the light rays, therefore it is positive. And you are measuring this distance below the principal axis, therefore it is negative. So once again I will repeat 4 conditions. So whatever you measure it from the optic center of the lens. If the measurement is done against the direction of the light rays, then it is said to be then it is positive, that is negative. If you are measuring anything along the direction of the incident light rays, then it is taken as positive. Whatever you measure above the principal axis, that is taken as positive, and whatever you measure below the principal axis, that is taken as negative. So these are the things you have to remember. So these are the sign conventions, right? So with this, we go with a very simple formula, that is lens formula. Keeping all these things in our mind, let us go with the lens formula, which is very, very simple. So here, the relation between U, V and F. The relation between U, V and F with respect to lens is called as the lens formula. Please remember this. What is lens formula? The relation between the object distance, the image distance and the focal length of the lens with respect to lens, any lens, that is positive, that is a concave lens or a convex lens, whatever it is. That formula is given by 1 by, that is minus 1 by U plus 1 by V is equal to 1 by F. So this is what we call as the lens formula. So that is minus of the reciprocal of the object distance plus reciprocal of the image distance is equal to 1 by focal length of, that is reciprocal of focal length of the lens taken, right? So this is what we call as the lens formula. The relation between U, V and F with respect to lens is called as lens formula, and the lens formula is minus 1 by U. You have to remember this. Mirror formula was not like this, it was 1 by F is equal to 1 by U plus 1 by V, direct formula. So here it is negative here, minus 1 by U plus 1 by V is equal to 1 by F. So this is what we call as the lens formula, right? So these are the very important things what we had to learn in today's session. So in the next session we will be going with the magnification of lenses and power of a lens. So both the concepts are very, very important, which is coming in the next section. So which are very much required for solving numericals on the lenses. Right? I hope you enjoyed the entire session. So everybody are telling you to stay home, stay safe, keep learning. Sorry to repeat that. So stay home, stay safe and keep learning. So it's already 13th of June today. So last date for the payment of the fees was 10th June. It's already 3 days are over. So still so many of the students have to pay the fees. So if this continues, I will not be able to run the show, because to make anything successful, any project successful, the support of the parents and support of the students is very much required. If you do not support the things, you cannot do it actually. So if some of the students have paid the fees, no doubt in that, I heartily thank them for the support. So I accept all the other parents also. Please pay the fees within the 2 days, that is 15th June. So maybe in the coming days, the video will be uploaded to the students only who have paid the fees. Right. So once again, complete the science notes. So in next session, we are going to come across the introduction for social studies done by one of our colleague of our institution. So please follow her, write down the notes, practice the problems on geometry, very important chapter of similar triangles. I hope you will make us proud at the end of the day. Thank you.